Hello everyone, my name is Mengxin Zheng. I'm a PhD student at Indiana University, Bloomington. Today I will present our work, Trojan VIT, Trojan insertion in vision transformers. To summary, we propose a stealth vision transformer specific backdoor attack. The top part shows the normal inference of a clean model. The bottom part shows that after flipping a few critical bits of the clean model, marked in red, the generated Trojan model misclassified the input with a trigger to a target output. Here, I would like to highlight that we have two main components, patchwise trigger and Trojan VIT insertion. Compared to CNN's capturing pixel-wise local features by convolutions, VITs extract global context information through patches and attentions. In this case, we propose a patchwise trigger. It adds trigger into divided patches. The trigger size is much smaller compared to area trigger in CNN. The poisoned patch is chosen by top patch ranking score. For Trojan VIT Trojan insertion, we use Rowhammer bit flip attack. For efficient attack, we further use parameter distillation to reduce bit flip numbers. Recently, we have seen the vision transformer success in various areas such as image classification, object detection, semantic segmentation, and image generation. However, there is a security concern with backdoor attack. Backdoor attack is very dangerous in CV tasks because it can mislead the model's output by attaching specific trigger into the input, which means benign samples work well, poisoned samples work under control. Moreover, CNN is known to be vulnerable to backdoor attack. Therefore, there is an initial question. Is vision transformer vulnerable to backdoor attack as CNN? To understand this, we conduct experiments with three triggers. In the backdoor attack on a VIT, trigger 1 and trigger 2 are area-wide triggers but have different positions on the input image. On the contrary, trigger 3 is a patchwise trigger. Different pieces of trigger 3 are embedded to different patches of the input image. Patchwise trigger has high ASR and much smaller trigger size. This is because CNN capture pixel-wise local features by convolutions. VITs extract global context information through patches and attentions. In summary, there are three challenges for our work. First, how to choose poison patches for patchwise trigger. Second, how to design stealthy trigger. Third, how to insert Trojan via Rowhammer. Correspondingly, we present three methods to solve these problems. For challenge 1, patch choice for patchwise trigger. We poison patch by patch silencing ranking score. If the trigger is in two patches, we choose top 2 score. The silence score GXI of a patch XI is the sum of the silence score of all its pixels. It can be computed by the absolute gradient of the cross entropy loss function over each pixel Xij. With a mask matrix M to produce the trigger P circle.M, the next step of Trojan VIT is to generate the perception P. Our goal is that the patches with the perception P in the trigger should gain more attention than the other patches having no trigger in the input. The attention function is a negative log likelihood of the sum of attention distribution of head H over T selected patches. After the trigger generation, we attack the model by Rowhammer bit flip for Trojan insertion. Rowhammer attack work by rapidly accessing physical rows in DRAM, which can cause bits in neighboring rows to flip. meaning 1 turns to 0 and 0 turns to 1. However, this kind of attack is heavily limited by the bit flip numbers. To reduce the bit flip numbers, we propose parameter distillation method. During training, for each epoch, parameter changes that are smaller than the specific threshold will reset to their original values. Only the parameters that have changed greater than the threshold are updated. The results of our Trojan VIT attack are shown below. Compared to prior attack works, our Trojan VIT achieves a high ASR, maintains a high clean data accuracy, and modifies fewer weight parameters. We can also see that the performance of our Trojan VIT improves with the proposed methods. In addition, our Trojan VIT shows different vision transformer architectures such as VIT, DIT, and swing transformers. That's all for the presentation. Please refer to our paper or the poster section for more details. Thank you.